In our previous video, we talked about the algebra of matrices, saw how we can kind of determine the dimensions of the matrix to set up augmented matrices, matrix equations, as well as doing matrix multiplication. Now, here we're going to shift gears a little bit and we're going to move to 9.5. And 9.5 is going to be on the inverses of matrices and matrix equations. So we're going to go back to these matrix equations we were talking about and try and solve these using our inverses, right? So with this being said, yeah, we talked about how, for example, in kind of ordinary algebra, we have something like ax equals b, and to solve for x, what we would want to do is something like b divided by a. So we would divide both sides by a. But we talked about with matrices, there isn't really a division process. So we have multiplication and we know how to do matrix multiplication. And so what we'll do instead is we'll rewrite this as actually a to the power of -1 times b. So we'll make it a multiplication instead of a division, right? And so if this is true, in typical space, right, like we said in algebra, ordinary algebra kind of process, we would, instead of dividing, multiply by a to the power of -1. Now this is not the inverse, of course, of a. This is just a to the power of -1. But with matrices, if we have ax equals b, we're now in the kind of matrix form, right? The conversion of this would be x is now a inverse b. So kind of a similar, notation at least, but it's now an inverse. Yeah, so this a inverse here, we are going to have to find the inverse matrix, so a inverse. So obviously we need to talk about how do we find the inverses. And so before we do that, right, but obviously this is the sentiment, this is what we want to do. We want to find the inverse of A, and then we will multiply A inverse with B to be able to solve for the variable that we want, or the variables, yeah, the variable matrix. So first we need to discuss the identity matrix before we do anything. So the identity matrix, which we will define as I to the n, where of course n is going to be the dimensions of the matrix. Remember here, with an identity matrix at least, these are going to be a square. Okay, so these are square matrices, and it will be obviously that dimension n. So these are square n by n matrices. And what we know about the identity matrix is the identity matrix is going to be ones along the diagonal and then zeros everywhere else, right? So what we notice is that this is kind of somewhat similar to if we just multiply something by 1 in like our ordinary algebra scheme. So, 1 times a would just be a. In similar fashion, I, whatever the dimensions is of my matrix, right, of a, if you multiply the identity matrix by that matrix there, you would just get back the original matrix. Okay, so kind of in a similar line of thought, we're trying to use the identity matrix as almost like a multiplying by 1. So when you multiply by this, it won't change the matrix itself. So as an example, the 2 by 2 identity matrix, which we'll label as I sub 2, would just be a 1, 0, 0, 1. If this was the 3 by 3, you would have 1, 0, 0, 0, 1, 0, 0, 0, 1, and this would go on, right? So same idea, you have ones on the diagonals, and then you have zeros everywhere else, right? So ones on the diagonals, and then zeros everywhere else, okay? So I should note that as we saw, I times A is the same thing as A times I, because if this is supposed to represent 1, the output will always be the same, no matter the order we do the multiplication in. Remember, though, that we talked about matrix multiplication not being commutative. That's still true, but for the identity matrix, you can multiply it in either order and you will still get the original matrix, right? Just because of the identity matrix being what it is, the multiplication will always come out to be this. But if this is obviously a different matrix, some a times b or whatever, that won't always be true, right? Okay. So from here, let's kind of shift gears, right? So we talked about this identity matrix. Now we want to go ahead and look at the inverse of a matrix, okay? So the inverse of a matrix. So here's what I'll say. A times A inverse will be the same as A inverse times A, and this will be equal to the identity matrix. So if you take a matrix and you multiply it by its inverse, or vice versa, right? You take the inverse of the matrix and you multiply it by the original matrix, you will produce the identity matrix, okay? You will produce the identity matrix. This is very similar to in, our kind of ordinary algebra scheme, you doing something like f of f inverse, right? Obviously this is not multiplication per se, but it's somewhat similar, right? You take a function and you plug in its inverse into that, right? You do a composite. This would be the same thing as f inverse of f, and that would just give you the original input, right? So this is somewhat like that, right? We can imagine a very, very similar kind of style where you take the function, you take its inverse. When those two things come together, they're supposed to almost, undo each other. And what we end up with is, in this case, the input, or in this case, just an identity matrix, okay? So something to know, obviously, about our inverses is making sure that when we multiply these together, that we will produce the identity matrix. Now, I should say that we are, a couple things. Not every matrix has an inverse. Okay, so not every matrix has an inverse. How do we know when something has or does not have an inverse? Well, first off, one thing is you have to be the matrix itself has to be square, right? So you have to have a square matrix. So matrix has to be square. If you don't have a square matrix, 2 by 2, 3 by 3, 4 by 4, you first off won't have an inverse, right? So in order to get an inverse, you need to have a square matrix. Okay. Now from here, I'll label this. So if it is invertible, I should say that the determinant of that matrix is not going to be 0. Okay, so if you want to have an inverse, you would need the determinant of that matrix to not be equal to 0, right? And we'll kind of go deeper into our determinants and things like that. But keep this in mind. We have some property here in the determinant, and we need to make sure that the determinant is not going to be 0. Or else we won't be able to find the matrix, right? If the determinant is 0, then you will not have a matrix. If the determinant is not 0, you will have an inverse, right? You have an inverse. This will come back in 9.6, so we'll come back to this. But okay, so we need to know these in mind. With this, we also know that if it is if it does have an inverse, I should say. So if we have an inverse, then we say that it is invertible, or we say that it is non-singular. Okay, so if you have an inverse, if we have a square matrix, its determinant is not 0, and it has an inverse, we call that invertible or non-singular. If it does not have an inverse, so no inverse, what we do is we call that singular. Wow, so non-singular when it has an inverse, singular when it does not have an inverse, okay? So again, kind of all this recap. So for an inverse, we can take A times A inverse or vice versa, and that should produce the identity matrix. Not every matrix has an inverse. The matrices that do have inverses are going to first have to be square. So if you are not a square matrix, you do not have an inverse. And it also has to have its determinant not be equal to 0, which we will obviously discuss what the determinant is and all that. But for now, just kind of think of this as some property we're going to be told or we will find, but the determinant has to be non-zero. Right? And then if it does have an inverse, we just say that that matrix is invertible or non-singular. If it does not have an inverse, so it's not invertible, we would say it is singular. Easy enough, yeah? Couple pieces of terminology. So one thing we might want to do is we might want to verify that two matrices are inverses of one another. So the question might say, hey, verify that B, which is 3, -2, -1, 1, is the inverse of this matrix A, which we will say 1, 2, 1, 3. Okay, so verify that matrix B is the inverse of matrix A. Now here we will compute AB and we will also compute BA, and we'll go ahead and prove that these are equal to the identity matrix, and therefore we have proven, of course, that the that these two matrices are inverses of one another. Yeah. So again, think back to what we have up here, right? Okay. So let's do it. So A times B. I'm going to just write these out. A times B. And then I'll just do the same thing down here while I'm at it, right? B times A. So remember with these, we're doing matrix multiplication. This is a 2 by 2. This is a 2 by 2. Same thing here, 2 by 2, 2 by 2. So what happens is we check the inner dimensions. The inner dimensions are the same for both, right? 2 and 2 and 2 and 2. So that means we can do the multiplication. And then the outer dimensions tell us the shape of the new matrix. So the new matrix will become a 2 by 2. So the new matrix will be this 2 by 2. So we'll have 2 by 2, right? So let's solve what these are going to be. So matrix multiplication, we go row by column. So the first item here will be first row, first column. So we do the product and then we sum the terms. So we will get 1 times 3 plus 2 times -1. That is 3 minus 2. That is going to be 1, right? 3 minus 2. Then we do row 1, row 1, column 2. This is row 1, column 2 right here, right? Row 1, column 2. So we will do 1 times -2. -2 plus 2 would be 0. Okay, we're looking like the identity matrix. Row 2, column 1. Row 2, column 1. That's this guy right here, row 2, column 1. So we go 1 times 3 plus 3 times -1. 3 minus 3 is 0. Yep. Row 2, column 2. Row 2, column 2. Row 2, column 2 right here. We get 1 times -2. -2 plus 3, positive 1. Cool. So this is the identity matrix, right? Do it again. B times A. 3 times 1 minus 2. 3 minus 2 is 1. 3, 2, 6 minus 3, 2, 6. 6 minus 6, 0. -1 plus 1, 0. -2 plus 3, positive 1. This is also the identity matrix. So therefore, A and B are inverses, right? So, or however you want to say it. So B is the inverse of A. If you want to say that, B is the inverse of A, since that's how we kind of labeled or worded it in the original problem. Okay, awesome, easy enough, right? That's just proving, using that logic, A times A inverse or vice versa is producing the identity matrix, very similar to us checking if two functions are the inverse of one another in kind of this ordinary algebra type scheme, f of f inverse or vice versa. All right, so let's keep moving on here. So we know about inverses, we know kind of how to get moving with proving things are inverses. I still want to figure out how to find an inverse. Yeah, we haven't talked about how to find the inverse yet. We just have talked about the inverse itself and some things about it. So we will now talk about row operations. Okay, we'll talk about row operations. And in particular, I'm going to talk about elementary row operations. Okay, so elementary row operations. So when we are trying to find the inverse, okay, we are going to perform what we call elementary row operations. So our main goal is going to be to take you know, some matrix we have, and in this case, generally it'll be an augmented matrix. And what I want to do is I want to transform this matrix to look like some other matrix, right? So I'm going to do some transformation, right? There's some stuff here, and I've gone and changed it. We're going to talk about what changes need to be made, of course, but we overall I'm just trying to change it. Yeah, make a transformation. It's similar to like if I give you a function and I want to do some transformations like shift it up, down, left, right, stretch it, shrink it, whatever. I do those in algebra, right? I'm going to do the same thing with the matrix. I'm going to try and transform it to change it and how it functions, how it looks, everything like that, and get this new output. Okay. So in order to do these transformations, you have to perform these elementary row operations. So right here, these would be row operations that you would need to perform to go from one matrix to a different matrix to kind of transform this. So what are the three elementary row operations that we are allowed to do? So when we do these, right, so I'll note that these operations here, we are only changing the appearance of the matrix, but we're not inherently changing the underlying information that it represents. What I mean by that is we're changing the look of it, but the solutions from this matrix are going to be the same. Yeah, so we're not like losing information or changing. Like if the solution was x is 1, we're now not going to have something where x is 3. Yeah, it will still be x is 1. You will solve the same information. So this might make more sense in a second, but let's talk about the three row operations, okay? So the first one is you can interchange any two rows. So think about this, yeah. If we think about our matrices as our systems, right? Because our whole goal was we were trying to take these systems of equations and we were trying to solve these using matrices. If you imagine that you've got some system where it's like x plus 2y equals 1, 3x minus y equals 4. If you were to interchange this equation in this one, so that you put this on top, for example, you haven't changed the system, right? The system is the same two equations. All you've done is rearranged where they are located, but it's the same system. Yeah, you haven't done anything. You just changed its appearance, but the system is fundamentally the same. This is the same for matrices, right? Because we're saying the matrices just represent this system. So if you change the order of the equations, it doesn't change anything about the overall system because the equations are still there. Yeah. So we can interchange any two rows. That seems pretty good, right? I feel confident that that's true based on just looking at my system. Another thing we can do is we can multiply a row. So we can multiply a row by a non-zero constant. Okay. So you can multiply a row by a non-zero constant. This also makes sense if you look at our system, right? So think back to our system up here. If I just went ahead and multiplied this entire system by 2, right, some non-zero constant, this is the same equation, yeah? So for example, y equals x and 2y equals 2x, this is still y equals x. Yes, the solutions are all the same. It just looks different because I've scaled everything by 2, but the solutions are all the same. It is the same exact equation if you were to graph it. And so in similar vein, right, scaling any of my rows by some non-zero constant will not fundamentally change that equation. It is the same equation. It just looks slightly different. And so this should make total sense that this is allowed, right? I can just modify one row by some constant, and that will just scale all the pieces so my solutions maintain the same answer. Yeah, it's the same exact equation, same exact system. Now the third one, a little bit more difficult to kind of see with our systems, but still we'll have this. So we will add a multiple of one row to another row. So what we can do is we can add a multiple of one row to another row. So that means I might take 2 times this row, and then I'm going to add that new thing to the second row, right? So I'll take my second row and I'll add to it 2 times the first row. So we can do that, and that will change the second row. We'll be able to modify those things. These 3 operations are operations that only change the appearance of the matrix, but it does not change the underlying information it represents. So what that means is it will change the look, it will not change the solutions. We will still have these same x, y, and z's or whatever we're solving for, right? If it's a 3D, x, y, and z, we'll still have the same solutions coming out of that system. Okay. Now, what I want to get at is, again, these row operations are kind of a process we perform in between, right? This is just some of the rules that are going, but we're using the row operations in between, going from starting matrix, we're starting augmented matrix basically to some new augmented matrix. And so let's kind of clarify that a little bit more here. What we're seeing is that using these row operations, our goal is we are going to try and transform the augmented matrix A augmented with I. So A is the coefficient matrix, I is obviously the identity matrix. We're trying to take this augmented matrix. We are trying to perform elementary row operations, and we are trying to then transform it to produce the identity matrix augmented with A inverse. Okay, so what we're doing, right, to find our inverses then, right, using these row operations, we will be taking A augmented with I, perform these row operations, and produce the augmented matrix to be in the form of I augmented with A inverse. And therefore we have our inverse, right? So we can read right off of this. This would be ones on the diagonal, zeros everywhere else. And then we'd see that on the right side, we've got some matrix. We'd pull those values. That would be our inverse, okay? Now, if you cannot get it in this form, right? So for example, if I cannot get the identity matrix on the left side, that means that I am not invertible, right? That means that matrix cannot uh, have an inverse, right? It does not have an inverse. I cannot find the inverse of that matrix. Um, Generally, you're not going to go through all of the row operations and then just at the end notice that you can't get the identity matrix, right? That's where we come in with the determinant. We said up above that, hey, the only way that we're going to have an inverse for the matrix is if the determinant is not zero. That's going to be what we rely on to figure out if we have our matrix being invertible or not. We will not obviously do all of the work, perform all of the row operations, and then at the end of all of our efforts, notice that the left side is not the identity matrix, and then we would have to say that it's not invertible. Generally, you need to make sure that there's an inverse before you solve it. Yeah. It's the same thing as when we talked about, hey, I want to check if the function's one-to-one before I go ahead and try and find its inverse, because it's not going to have an inverse function if it is not a one-to-one function. It's the same logic, yeah? You want to check before you do anything that you actually have an inverse, okay? Okay, so this is kind of our plan here, yeah? Now, what I want to note is that as we go through this process, the row operations, you will have to choose which you want to do, right? There's no set way to do it. Yeah, you as the person solving it get to determine the order you want to do, what operations you want to perform. So we will need to look at perhaps some best practices on how to do this in as few steps as possible, right? You don't want to have to do like 10 steps when you could do it in like 2 or 3 steps. Yeah. So you want to get good at kind of recognizing certain things that you should be doing, I guess, as we go through. So we'll talk about that and we'll do a couple practice problems. Right? Now, one thing I do want to note is because we're taking this matrix and we're augmented matrix and we're trying to turn it into this one. On the left side, you see that there's the identity matrix. We, in a sense, don't necessarily need to have the identity matrix. So this will be two different ways that we're solving our our systems, I guess. But with inverses, you need to have the identity matrix here. Okay, so in the case of solving for inverses themselves, you would need to do that. But in general, when you're just doing row operations, there's kind of two ways that we would do this. So one way, and I'm going to kind of label these, is we could get row echelon form. You can get a matrix in row echelon form, or you can get it in reduced row echelon form. Okay. So let's talk about each of these. So row echelon form has a couple conditions. So we're going to talk about the conditions here. Okay. So with row echelon form, the first thing is you want your first non-zero entry, or I should say like entries, but you want the first non-zero entry in each row. The first non-zero entry that you have is known as the leading entry. It makes sense, right? It's the first number, it's the leading thing. So the leading entry, you want that to be a 1. Yeah. So every non-zero entry in every row you have, so that is your leading entry, that first number needs to be a 1. Okay. First non-zero thing has to be a 1. Second, you want each leading entry in a column. So you have each leading entry. That's going to be in a column to the right of the leading entry in the previous row. Okay. So what that means is the leading entry. So let's say I have 1, 0, 0 here. Yeah. The leading entry is in a column that's to the right of the leading entry of the previous row. So this is the first row. This is my leading entry. That means in order to be in row echelon form, the next row would have to have a leading entry that is to the right of this entry. So that means there has to be a 1 here, for example, or even a 1 here. That would be in row echelon form, right? So you cannot have a 1 here. This is not going to have the next leading entry on the row below it being shifted to the right in a column, right? That this is not going to be, for example, if I had this is not row echelon form, but if I had this, that is row echelon form. Or even if I had this, that is row echelon form because this leading entry, well, I guess that should be a 1, right? I need the leading entry for this part, but you get what I mean. This has to be shifted to the right of the leading entry in the previous row. Okay, so this is to the right. That's cool. Okay, hopefully that makes sense. So I got these two. The third one is that rows with all 0 elements, if there are any of those, right? Sometimes you don't have all zeros and you just have normal, values across the row. So if there are rows with all 0 elements, if any of those are going to occur, you want to make sure that those are below rows having non-zero. I should call these entries as well, right? So I'm saying elements, but the same idea, right? So rows with all 0 entries, if that does exist, are going to be below any rows that have non-zero entries, right? So anything that has numbers that are not 0, you will want that to be above anything that has all zeros. The more zeros, the further down we should kind of be going, right? All right. So this being said, what about reduced row echelon form? Well, row echelon form is not too bad. But what we notice with row echelon form is you can have something like this. So for example, you can have a matrix that is, let's say, 1, 2, 3, 0, 1, 4, 0, 0, 1. And what this means is that if this is our matrix, right? Think about this is the coefficient matrix. This is equivalent to x plus 2y plus 3z. And obviously this might have like another matrix on it, right? This might have a coefficient matrix is just the A matrix, the coefficient one, and we might have x, and we might have equal to, and the actual solution, what it's equal to, right? The constants. But I'm just showing you the coefficient matrix for now. So this might be this equals whatever, some number, right? I'm going to leave these blank because I haven't said that yet. The next row tells you that y plus 4z equals some number. And then the third row tells you that z equals some number. So in this case, with row echelon form, what we're noticing is that you can solve this system currently, right? So you have z, you plug that into your second equation here, and you can solve for y because this is a known now. And then once you find z and y, you plug that into the first equation and you get x, and so you have x, y, and z. So in this kind of process, you can back substitute, right, and solve your system. This is what we call Gaussian elimination. Okay, so if you're trying to solve your system for the variables, right, x, y, and z, if you get something in row echelon form and you solve your system, that's solving it using what we refer to as Gaussian elimination. So the row operations, I'll say in general, like we are just always going to do row operations, so I wouldn't get too nitpicky on the names. But Gaussian elimination means that we're going to do row operations where the final solution that you have, the final like matrix you produce, has these characteristics, right? And so this requires back substitution to solve, right? Because you have to take this, you have to back substitute it into a previous equation and solve for that, and then you have to take those and back substitute again. So with Gaussian elimination, we get our matrix into REF, right? So we can label this. This is REF, row echelon form, and then we solve. Okay. Whereas reduced row echelon form, I'll note here, first characteristic is the same. So I'm gonna say like repeat. Yeah. So the first to be in reduced row echelon form, you first want the leading entries to be ones. Two, you're also going to repeat this. So you need to have leading entries shifted to the right. And then three, you need the entries above and below the first one in each row must be, or must all be, I should say. They must all be 0. So what that means is when you look at this over here, right? So this is in REF right now. To be REF, you need entries above and below R1 or leading entries. I need those to be all zeros. So in this case, this one has all zeros below it. That's great. That it would be okay for what we want. But here, this one does not have a 0 above and below. It has the 0 below, but it does not have the 0 above. So you need to turn this 2 into a 0. And then you'd also need to go here and turn these 3 and 4 values. You need to turn those to 0. So basically these need to become zeros, which is going to be basically the identity matrix, right? If these are becoming zeros, then you have ones on the diagonal, zeros everywhere else. You would be producing the identity matrix. So this is kind of very similar to what we were getting at up here. This is, in essence, you can think of it as reduced row echelon form, right? So getting this kind of process would be this second way to do it. And with this, with REF, right, reduced row echelon form, we call this Gauss-Jordan elimination. Okay, so instead of Gaussian elimination, we call this Gauss-Jordan elimination. This is just obviously from the the people who kind of are attributed to this process, right? So Gauss and Gauss-Jordan, these are different people who came up with this process of this elimination. Okay, so we will, of course, not go too crazy on these terminologies, right? Like row echelon, reduced row echelon, or Gaussian or Gauss-Jordan. Just something to kind of think about. I wanted to put it up here, but we'll be focusing a lot on just doing the row operations up here to go from A augmented I to I augmented with A inverse. Okay. So this is going to be just our main focus. We don't really need to have too much focus on these words. It's good to know these, yeah, but my focus is not on this. My focus is on, can we actually just perform the row operations and go from here to here? Yeah. So let's do an example, okay, where we actually perform these row operations. We haven't done any examples like that yet, but we're gonna do one now. Note that when we do these row operations, you will need some space. Yeah, you'll need some paper. You'll need some room to be able to do this out. So be prepared if you're writing this down. Make sure you got some paper with you. Okay. So here's what we're gonna do. We're gonna take an inverse. Or sorry, we're gonna find an inverse. I'm gonna give you a starting matrix, which will be A. So 1 0 0, 2 1 0, 3 2 1. And what I'm gonna do is I want to find A inverse using row operations. Okay. And what I want to do is, as I go through, I need to document this. I need to show every single operation I'm going to perform, and obviously where how am I doing the transformation, right? You can't just say, okay, this is here, and then you give me A inverse, and then you say you're done, right? There's no way to know how you got from there to there, and you need to show me the work. Okay. So here's what we're gonna do. We're gonna first produce A augmented with the identity matrix. Yeah, we're gonna first produce this. So this is 1 0 0 2 1 0 3 2 1 augmented with 1 0 0 0 1 0 0 0 1 0 0 1. Okay. And so what I'm going to do is, remember, I'm now trying to convert this into the identity matrix augmented with the inverse. So I need to somehow get this left side to look like the identity matrix. Yeah, that's my goal. I need this to start to look like this. And so to do that, think about this. We have ones on the diagonal already. That's awesome. I have zeros up here. That's also good. The only thing left to do is I need to make these zeros, right? So in order to get the identity matrix, you have ones on the diagonal, zeros everywhere else. You already got zeros here. These need to also be 0. Generally, when you do row operations, your goal should be to make the bottom right-hand side become zeros. Okay, so in general, even if you had numbers up above here, right, these were like 5, 2, 3, whatever, I generally wouldn't tackle this first. You can do whatever, right? Again, this is at your discretion how you want to solve these. But in general, a good starting point would be to make the bottom left-hand side values become zeros. Okay, that's the general process we're going to solve here. So I want these to be zeros. And so how am I going to do this? Well, think back to row operations. I'm going to come back up here just to refresh us. We have 3 elementary row operations. We can interchange any 2. We can multiply any row by a non-zero constant to scale it. And then we can add a multiple of one row to another. The third one is going to be the one we use most often. Okay, so multiplying one row by something, and then we add that multiple to a different row, right? So let's look down here. I wouldn't want to interchange everything, right? This is looking like the first row I want, ones with zeros there. This is also looking where I want. I just need this to be 0, 1, 0 instead of 2, 1, 0. So this, I wouldn't want to interchange any of these rows, right? It doesn't make sense. It already looks close to what I want. I also don't want to scale anything up right now because it's not going to do too much for me. I mean, we could scale some stuff, but we need to think about being strategic on that. To me, look at these values and look at these values. So ideally, when you do these row operations, you want to use the rows with the most zeros, right? The reason for this is because think about using this for anything. You do not have a y and z, right? If you're thinking about this as corresponding to x, y, and z in an equation, right? 1x, 0y, 0z. You don't have y or z, which means you have all the flexibility to just scale x alone, right? So if I wanted to cancel out something with x, because these don't have anything in it, these will not affect any of the y and z values over here, because you would be adding or subtracting 0 of those things. So the more zeros you have, the less you will impact the other rows, and that's good because that means you can more specifically target what you want. Yeah, so like this row will help me to specifically only target the first column, the first coefficients that correspond to x. So I'm going to focus on this, and I think I want this to be a 0. That was what we kind of said. Obviously I want all of them to be 0, but I think we could start with this one. So to make this a 0, what I could do is I could take row 2 and then just subtract 2 of this row, right? Because then I could take 2 minus 2, yeah? So if I take row 2 and I subtract 2 times row 1, I will get 2 minus 2, that'll go away. And then 1 minus 0, easy. 0 minus 0, okay, those don't change, exactly what I want, right? I don't want to change the things that are already good, that I already have. So here's how you'd write this, right? You'd say, hey, I'm going to take row 2, and I'm going to turn row 2, right? I'm going to transform row 2. So row 2 is going to become row 2 minus 2 row 1. Generally, what I sometimes do is I don't put this first part, I just write this. And so in this notation, I'm implying that row 2 is the row that you're modifying because it's the first thing I have. Just to be very explicit, we could write this, right? So it says row 2 is being transformed into row 2 minus 2 row 1. So this is the new thing that you're going to replace row 2 with, right? So if that were true, yeah, that was my process here. What you will do is you will take the original matrix and you'll keep everything the same other than row 2, right? I'm changing row 2. I just said that I'm making row 2 be this new thing. So every row other than row 2 will stay the same. You will not modify anything other than row 2. So I write row 1 and I wrote row 3 as row 1 and row 3 are. And then you will just update row 2. And row 2 will be, like we said, row 2 minus 2 row 1, 2 minus 2, 0, 1 minus 0, 1, 0 minus 0, 0, okay. Row 2 minus 2 row 1, 0 minus 2 is minus 2. 1 minus 0, 1, 0, 0, 0. Right? So you just perform the row operation. Yeah, you go through row 2 minus 2 row 1. I replace row 2 with that. And then I will do it again. Yeah, I will look at this and I will say, what do I want from this? Right? What's my outcome? And what I notice is that first two rows look great. 1, 0, 0, 0, 1, 0. I still need these two to be zeros. Yeah, I still need these two to be zeros. So what I could do is I could actually repeat the same exact process I just did using row 1, right? And I could say, hey, I want this to be a 0. Let's use this to get that to be a 0, right? Because these will not impact these numbers, which is good. I want this 1 here. Obviously, I need to change this soon, but we're going to use this row 1, to modify our row 3. So this is the thing I want to change, yeah? I want to get this to be a 0. So what I'll say is, I'll say, hey, I will take row 3, and I'm going to transform it into being row 3 minus 3 row 1. So row 3 minus 3 of this, 3 minus 3 would be 0. That's getting me where I want to be. Yep. So let's do this. You write the matrix again. Remember, I talked about having some space. You're going to need space in your paper. I am not changing row 1 or row 2. Those are staying the same. So row 1, row 2, I am now modifying row 3. Row 3 is becoming row 3 minus 3 row 1. 3 minus 3, 0. Row 3 minus, okay, that's just 2, right? 2 minus anything is 2. 1 minus 0, or sorry, not 2 minus anything. 2 minus 0 is just 2, right? 1 minus 0 is 1. 0, row 3, minus 3, row 1 would be 0 minus 3, 0, 0, 0. 1 minus some scalar of 0 is just 1 minus 0, which is 1. Okay, almost there, right? Almost there. So last thing I need is I need this guy here to be a 0. Yes, 1, 0, 0, 0, 1, 0, 0, 0, 1 is what I want. So last step, yes, last step. We will say, okay, need to modify this. Need to modify row 3. So I need to modify row 3. Row 3 is going to become row 3 minus 2 row 2. Minus 2 row 2. The only row that has a value in the second column that I can use to get rid of the 2 in the second column here is row 2. So I have to use row 2 to get this to be a 0. If I do that, again, I don't change row 1. I do not change row 2, right? I'm only modifying row 3. So row 1 and row 2 are staying the same. And row 3 is becoming what? Well, here we go. Let's do this. Row 3 minus 2 row 2. Okay, 0 minus 0 is 0. 2 minus 2, 0. 1 minus 0 is 1. Negative 3 minus 2 times negative 2 would be negative 3 plus 4. That's a 1. 0 minus 2 times 1 is minus 2. 1 minus 2 times 0 is 1. Okay. So again, just doing this exact thing and figuring out what the new row is. Yeah. So we get this, and therefore this is the identity matrix. 1's on the diagonal, 0's everywhere else. This is augmented with the identity matrix, because that's what we said we were solving for, right? Wherever we get the identity here, the right-hand side is the augmented matrix, the right-hand side of my augmented matrix is the inverse. And so I say A inverse is 1, 0, 0, negative 2, 1, 0, 1, negative 2, 1. This would be my answer. Yeah? This would be my answer. Okay. Hopefully this is making sense. Yeah. We have I augmented with A inverse at the end, right? And we get our inverse just from that. So A augmented with I, we transform it using elementary row operations into I augmented with A inverse, and then you just read it off to get your answer. Great. Okay, so this would be kind of a flow. Obviously, here we are making the decisions on what row operations to do. And so that's up to you, right? You want to be strategic on how you kind of approach these. As you can see here, my best, I guess my best advice is to focus on making the bottom left-hand side being those identity, or being zeros, right? So the quicker I can make that bottom left-hand side turn to zeros, the more flexibility I'll have, because I will have lost, the more zeros means the less information you carry on every time you do an operation, right? Particularly the multiplying a row by value and then adding that to another one. The more zeros, the better, yeah? Because you can change more specifically certain columns without having to worry about the other values. So keep that in mind. That will be helpful as we go along. And there will be plenty of practice that we'll do. I'm probably going to do a little bit later down the road on this. I'm not going to do another one here, at least. We'll kind of move on. But I would continue to practice these and try and get comfortable with making, obviously, the decisions, what operations to do where. Okay? Okay. So let's take this. Okay. Now, note we were just finding the inverse. I didn't actually solve like a system yet. We're going to get there in just a moment. But for now, I just gave you a matrix and I said find the inverse. We're still going to talk about how do I take that inverse and go ahead and solve this, which we did kind of talk a little bit about above, but we're going to hold off, right? So we're going to do some process like this, yeah, in the end. I'm not there yet, but our goal is the inverse is just part of the bigger picture. Okay. All right. So with this, I want to quickly note the inverse of a 2 by 2 matrix. So with a 2 by 2, there's actually a slightly easier formula. You don't have to necessarily do all of these row operations, although you could do row operations for a 2 by 2. You generally don't want to. A 2 by 2 has a nice easy formula to find the inverse. And so if we ever are working with 2 by 2s, it's highly encouraged that we follow this process as opposed to the row operations. But again, it is up to you. It's at your discretion how you want to solve these things. Okay, so here's what we have. So given a 2 by 2, A, B, C, D, that's our matrix A, a 2 by 2. What I will find is that its inverse is equal to 1 over the determinant of A. So back to this kind of conversation of the determinant, right? 1 over the determinant of my matrix times D A negative B negative C. So what we see is that, at least for this new matrix here, right? It is very similar to the original one. All we do is the diagonals here, A and D, you flip them. So A and D get replaced with one another. And then across this diagonal, you just negate those. So you put a negative sign in front, and you just change the sign there. Yeah. So flip these, negate those. Right. Now, what about all this in the front, right? What about this scalar that we have here? Well, this determinant of A, right? This determinant of A, we talked about the determinant a little bit before. The determinant, so determinant for a 2 by 2 at least, right? So this determinant is just kind of this property we have. For a 2 by 2, the determinant is AD minus BC. So it is AD minus BC. Again, you see these diagonals, right? So we're taking the diagonal as normally we did here, and then you see this one, that one kind of got subtracting, negatives on this process as well. So that maintains too, right? AD minus BC, that's what the determinant is. So our formula is then 1 over AD minus BC of D negative B negative CA, right? This is the new matrix. So whatever this is going to be a scalar, right? It's going to be a constant. You're going to multiply that by every term here, and you're going to just see what the output is. But you get a new 2 by 2 that's just been scaled by this, and these are all flipped around. This would be your inverse. Okay. Note that if this is equal to 0, then you have no inverse. That's what we talked about last time, yeah? So earlier up above, we said If your determinant is 0, you have no inverse. Or if your determinant is not 0, then you have an inverse, right? So if it is equal to 0, you will have no inverse. Okay, so as an example, let me do this, right? Instead of, again, doing row operations, finding the inverse, we can just use this formula if it is a 2 by 2. So let's say I have matrix A, which is a 4, 3, 2, and 2, and I want to find the inverse, A inverse. Well, the inverse is going to be this, right? It's going to be 1 over AD minus BC, AD minus BC, and then it's going to be multiplied by the matrix where A and D get flipped and B and C are negated. Again, I'm just using this process, right? So go through, make sure that this all makes sense to you. All I'm doing is plugging in. Therefore, I get 4 and 2, 8, minus 2 and 3, 6. So this would be a half. 2, negative 3, negative 2, and 4. Therefore, my inverse would become 1, negative 3 halves, negative 1, 2. This would be my inverse. Okay, so this is the final answer that we're looking for there. Okay. Again, I think this is pretty straightforward, right? We have this formula for a 2 by 2. When we have a 2 by 2, it's much easier to just use the easy formula than go through and do all of those row operations again. Generally, you only want to do the row operations if you have higher dimension. Yeah, 3 by 3, 4 by 4, and potentially higher, right? We're not going to do higher than likely a 4 by 4 in this class. Generally, we stick to 2 by 2, 3 by 3s, but we could maybe go up to a 4 by 4. We will never go higher than that. Yeah. But there are obviously plenty of reasons why we would, and in their real world situations where something of higher dimension makes perfect sense, right? You're not going to be dealing, probably with systems that are just 2 by 2s. That's a simple solution. You probably aren't even using matrices to do that. But yeah, something to keep in mind, okay? So 2 by 2, we know how to do there. Now, let me come back to what we were talking about before. So my end goal has always been to solve some system, right? And the system we have gone ahead and turned into this kind of matrix equation. And so our goal is really to solve these matrix equations, okay? So we took our system, and remember, we produced AX equals B, yeah? So AX equals B, this was the coefficients, this was the variable matrix, and this was the constant matrix. So we took all the pieces of the system and we put it into this matrix equation here. Now my goal here is, as we said, we want to solve for x. And so our process here is we kind of take A inverse and we multiply both sides by this. So A inverse B. And the reason we do this is because, remember, we talked about the property A inverse times A produces the identity matrix, right? And anything times the identity matrix is just the matrix itself. So this I times x would just be actually x, and therefore I end up with A inverse B. So this is how we solve this matrix equation, right? So x will equal A inverse B. And so all of our efforts have been focused on finding this. Now, once we have this, we will take that and multiply by B, the constant matrix, and we will be able to have our solution for the variable. Okay. Note that the order I did this in is very important. So here, A inverse has to come first in the multiplication process because, again, multiplication for matrices is not commutative, which means x is not equivalent to B A inverse, right? It may be true for a specific case, but in general, this is not, this and this are not going to be equal, right? It's not true that you can move the matrices around. So keep that in mind. You always want to do the correct formula, okay? So what I will do is I will talk about this process for a 2 by 2, and I will talk about this process for a 3 by 3, okay? So we can make sense of this. So let's say a 2 by 2 case is I have the system x plus 2y equals 5, and then I have x plus 3y equals 8, okay? Converting this into a matrix equation, this would be a 1, 2, 1, 3 times xy equals 5, 8, right? That would be the matrix equation. So we take the coefficients here, right? We take the variables, x and y, we put in that matrix there, And then we put the constants in this matrix. Okay, if you did matrix multiplication, you would get 1x plus 2y equals 5. 1x plus 2y equals 5. And then you do the same thing with this row and this column. You get the same result, right? X plus 3y equals 8. Okay, so from here, we need to find its inverse, yes? So as you see, x is equal to a inverse b. So we will find its inverse. So here, to find the inverse, you either do a augmented with I, converted with I, right? Converted to I augmented A inverse. We could do that, right? Or I'd probably want to use my 2 by 2 formula, right? A is a 2 by 2. So I would love to just do 1 over the determinant of AD get flipped, B and C get negated. So I'll do that, right? That's what I'm going to do to solve my my system here, right? I'm going to look at my A, which I could plug in here and kind of get its inverse. Or what I could do is I could just use that to kind of plug into this, yeah? So let's do that. I will get, change my color here, A inverse is therefore 1 over AD minus BC, so that's 3 minus 2. Well, I'll just write it out so we can see it here, I guess. And this becomes 3, 1, negative 2, negative 1. So I get 3 minus 2, which is 1, so the coefficient is just 1 here, so it's 3, negative 2, negative 1, 1. That's my inverse. And so if this is my inverse, to actually solve this then, I go x equals A inverse B, which A inverse is 3, negative 2, negative 1, 1, and B is 5, 8. Matrix multiplication, row by column, what do you get? Well, this is a 2 by 2, and this is a 2 by 1. Inner dimensions match. Outer dimensions tell me this would be a 2 row by 1 column, which makes sense because you're solving for x and y. It should look like that matrix, which is a 2 by 1. So the 2 by 1, we get 3 times 5, 15, minus 8 and 2, minus 16. 15 minus 16 is negative 1. Negative 5 plus 8 would be positive 3. That would be my solution, or simply put, x equals negative 1, y equals 3, right? That would be my answer. Now that makes sense if we go up to our system here and plug in x is negative 1, y is 3. Negative 1 plus 6 is 5. Negative 1 plus 9 would be 8. Both of those are true, which means this is indeed my solution. Okay? So that is a process when we do a 2 by 2. We use the inverse to, again, solve that matrix equation that we had from the 2 by 2 matrix here, A. If I wanted to do a 3 by 3, I would have to obviously get the inverse using the row operations. What I'm going to do is, for the sake of this, I'm going to use an example that we already did. So up here, right, this was the A that we solved for, and we got this as its inverse. So what I'm going to do is I'm just going to use this as my example. Okay, so I'm going to make a problem where this is the equation we're solving for. That way we don't have to do this whole row operation process again. Okay, so I will go down here. Let's say now we've got the example where we're solving the okay, it didn't copy. Let's try this again. So I want this here. Okay, great. So let's say now we are doing the example of a 3 by 3 or onward, right? So this is just a 3 by 3, but it could be a 4 by 4, whatever. You just solve this. So we did all of these operations. Again, I'm just going to take the final answer of what we said we had. I'm not going to solve this again. We already did the row operations, but I found that for this equation, I found its inverse was this. And so the original, right, this original system might have been something like this. So let's say it's x, 2x plus y, 3x plus 2y plus z. And then I have to give these values, right? So these are just the coefficients of all of this. So this could be the system, and then maybe this is like 3, 1, negative 2, let's say, right? Using the fact that I have this inverse now, so I will take this, right? I have ax equals b, so I could do, 1, 0, 0, 2, 1, 0, 3, 2, 1, a, and then this is x, so this is x, y, z equals 3, 1, negative 2. So this is A, x equals B. I'm now going to create x equals A inverse B since I've already found the inverse. So x, which is this, x, y, z, equals A inverse 1, 0, 0, negative 2, 1, 0, 1, negative 2, 1, pulled from up above, times B, which is 3, 1, negative 2. And I will go ahead and solve what x, y, and z is just by matrix multiplication. Okay? So here, again, since I already did the inverse, it saved me some time. But if this was a normal problem, you would have to do the row operation process yourself, right? You'd have to go through all the steps. And then once you had that, you take a deep breath, you collect yourself, because we just spent a lot of time doing that. And then you do the final matrix multiplication to solve your matrix equation, right? So what I get here, let's see, I do A inverse of B, yes? This is a multiplication. I go row by column. So I get 1 times 3, 0 times 1, 0 times negative 2. I add those up. That's just 3. Negative 2, 3, 6, 1, 6, negative 6 plus 1, and then 0 is negative 5. 1 and 3 minus 2 is 1. Minus 2 again is negative 1. So therefore, we get x equals 3, y equals negative 5, z equals negative 1. This would be my solution to this system. And we should check it, right? You plug in x is 3, 3 equals 3. Yep. Plug in x is 3, y is negative 5. 3 times 2 is 6. Minus 5 would be 1. Yep. Plug in here. 3, 3, 9. Minus 10, negative 1. Minus 1, negative 2. Yes. Cool. So this does work. These are going to be my values for my variables, x, y, and z. Awesome. Okay. So hopefully all of this is making sense. Of course, there is going to be some work that has to be done on getting good at row operations, yes. But hopefully in this video, the general sentiment of how we go about solving these, why we need the inverse, and some best practices on how to do the row operations. Hopefully this is all making sense to you. Keep practicing, do a couple problems. Again, focus on obviously these 2x2s and 3x3s. If it's a 2x2, use the formula to find the inverse of a 2x2 involving the determinant. If it is a 3x3, for now, we will be doing the row operations. Okay? All right, we'll wrap up there.